Hello all, let's start part 2 of section 1.4 and part 2. Our main goal is to learn the Pythagorean identities. Usually we are not teaching this part in other books until we talk about the unit circle. But here in your book they brought it in section 1.4. I will try to somehow do some proof for you. Even I know maybe it gets a kind of question why, for example, he's choosing r equal 1. But later when we go to chapter 3 and we start with the unit circle, you will understand why I choose r as a 1. Okay, before Pythagorean theorem, or before I explain to you the Pythagorean identities, how many of them we have and what are those, before that I'll just change the slides a little bit. I will talk first about, let me go to this side even, I'll talk first about quotient identities. Let's learn first this one, then we go to Pythagorean. Because if I want to show you a little bit of proof, right, from where this identity comes in and why we call it identity, then you don't need to memorize it, you will learn it if you know the concept, correct? Let's talk about quotient identities. First of all, what is an identity? You heard this word before when you were in algebra classes, even starting from last part of beginner algebra, then those of you that you had intermediate algebra or college algebra class, all the time, sometimes we are talking about identities. For example, when you write a plus b all square equals to a square plus 2ab plus b squared. In algebra, we call this one an identity. Or when I'm writing x squared minus a squared equals x minus a times x plus a, we call this identity. Then what is the meaning of identity? Which kind of equations we call them identities? The equations that for the given value of their variables, if you plug in those values in your equation, correct? In your equation, and both sides of the equation, and both sides becomes equal to each other, we call it identity. For example, let's say the easy one, x plus 4 equals x plus 4. For any value of x that I'm choosing for x, starting from negative infinity to positive infinity, any value that I choose for x, for example, if I choose for x 1, correct? If I plug in 1 on this side, and if I plug in 1 on the other side, both sides becomes equal to each other. That's why we call such an equation an identity, correct? It was a bit extra lecture about identities because when I start here with trig identities, I don't want to see that my students have a question, what does this identity mean actually, correct? Now, what are quotient identities? The first one is if you divide sine of theta, looking to the triangle to your left of your screen, by cosine of theta, it gives you tangent of theta. We call this one a quotient identity, or you can say tan theta equals sine theta over cosine theta. If you say no, let's prove it. The proof is really easy. Looking to this red triangle on the left side of the screen and previous lectures, we know that sine theta equals y over r, correct? And also we know cosine theta equals x over r. Also we know tan theta equals y over x, correct? Let's replace sine theta, cosine theta, and tan theta in this given equation, which is sine theta over cosine theta equals tan theta. Let's replace them in terms of x and r. Let's use the right side, correct? Here I have sine theta. Instead of sine theta, I will write y over r. Instead of cosine theta, I will write x over r equals tan theta y over x. Because we prove, I'll put a question mark. Is this equal to this? Let's simplify our left side. It's again a complex fraction. You can say y over r, change the big fraction bar to times, and flip the denominator, which gives you r over x. Is this equal to y over x? You see here r cancels out with r. You end up y over x equals y over x. Then I can say the first quotient identity is sine theta over cosine theta gives you tan theta, correct? We have to memorize this always. Or maybe in future I will say, okay, replace your tan theta, write your tan theta in terms of sine and cosine, correct? Immediately you replace tan theta with what? With sine and cosine. The next one is cotangent theta equals cosine theta over sine theta. Again, if you want to see the proof, I will use the same method. Cotangent theta was what? Cotangent is the reciprocal of tangent, which is x over y, correct? Is this equal to cosine theta was x over r over sine theta y over r. Again, simplify the right side. X over y. Is this equal to x over r times r over y? These two cancels out, and clearly you can see x over y equals x over y. And you see, like in the beginning when I explained to you that identities, both sides of the equation becomes the same thing or have the same value, we call it identity. You saw the proof here. Then your next quotient identity is this. Always you can replace cotangent theta in terms of cosine and sine, cosine over sine, or if you see somewhere you have cosine theta over sine theta, you can replace it with what? With cotangent theta, but based on what you need, correct? Now, when I'm done with this part, let's talk about Pythagorean identities, correct? From school, you know the Pythagorean theorem with the right triangle that you see on the left side of my screen, that the square of the hypotenuse equals the square of the two right legs, correct? A square plus b square. Now, let's apply this Pythagorean theorem on this given angle in a standard position, correct? Then I can write like this, that r squared equals x squared plus what? Y squared. It's the same thing. Okay, now If I choose the value of R1, please at this time don't ask me why 1. I will explain it in chapter 3 why we choose R as a 1. But here just accept if I choose R as a 1, this equation, if I name it equation number 1, this one becomes x squared plus y squared equals 1 squared. It means x squared plus y squared equals what? 1. Now, few more things, because I want to prove something for you. And in the slides, in the canvas, you will just see the identity, no proof. But here I'll do a little bit proof for you. Look, here we know that sine theta equals y over what? R. And because R is equal 1, then you can say sine theta is equal y over 1. It means your sine theta is equal y. It means instead of naming y is actually your sine of your theta. Correct? Same way, cosine theta equals x over r. And again, you can say cosine theta is x over 1. It means cosine theta is equal to x. Correct? I'll box this one and I'll box this one. Sine theta equals y, cosine theta equals x. I'll box these two and I'll replace my x and y in this equation with sine theta and cosine theta. Correct? Instead of x squared, I can write cosine theta square. Correct? Plus, instead of y, I can write sine theta square equals what? 1. Instead of writing cosine theta square, you can write in trigonometry like this. Cosine square theta. They are the same. Plus sine square theta equals what? 1. Or you can put it in a nice order. First sine, then cosine. You can write sine square theta plus cosine square theta equal 1. Most of you may know this identity, the famous, the first number 1 identity. The first identity that the students learn in trig is sine square theta plus cosine square theta equal 1. And you know the reason now why, at least a little bit. When we go to unit circle, you will know it, y equal to 1. This 1, I can explain it there, why. Okay? This is your first Pythagorean identity. We call sine square theta, I forgot to put a theta there, sine square theta plus cosine square theta equals 1 is your first identity. Now, copy this equation again here. Sine square theta plus cosine square theta equals 1. Let's name this one equation number 1. Let's divide all terms of this equation number 1 by sine theta. Or let's first divide by cosine theta, go in order, correct? I will divide all terms by cosine square theta. You can do this when you have an equation, right? I will divide here cosine square theta, I will divide this term with cosine square theta, and I will divide this term by cosine squared theta. Let's see what's happening. What is sine over cosine? Today you learn in this lecture that sine over cosine, you can replace it with tangent, correct? Then in terms of sine, instead of writing sine square theta over cosine square theta, I can write tan square theta, correct? Plus these two cancels out, you will end up with 1 equals, what is 1 over cosine? Reciprocal identity, we covered it in the first part of this lecture. 1 over cosine is secant, correct? Because you have a square, you can call this one secant squared theta. I will put this one also in a red box. This is identity number 2, correct? Same way, copy equation number 1, which I have sine squared theta plus cosine squared theta equal 1. This time I will divide all terms by sine squared. Then this one becomes divided by sine squared theta. This one divide by sine squared theta. And this one divide by sine squared theta. Correct? These two cancels out. Then you can write 1 plus cosine over sine was cotangent. Then cotangent, because you have a square, cotangent squared theta equals 1 over sine was cosecant, right? Because you have a square here, cosecant squared theta. I will put this one also in a red box, identity number 3. But we call all of them Pythagorean identities. Why Pythagorean identities? Why all of them? Because you see all of them comes out from equation number 1, correct? You have 3 Pythagorean identities. Even I can write 2 more for you. These 2 is also important. It's not in the slides. I think they want to cover it later somewhere else, but because we have our identities ready here, let's write the other 2 also. Again, you see, you have sine squared theta plus cosine squared theta equal 1. Let's solve this equation for sine. To solve this equation for sine squared, I'll subtract cosine squared from both sides. Cosine squared theta, also subtract here cosine squared theta. Correct? These two cancels out. Then I can say sine squared theta equals 1 minus cosine squared theta. Even if you want to find the sine here, you can write sine theta equals, take the square root from both sides. Let me show it for you. Take the square root from this side, take the square root from this side, correct? These two cancels out. Then you can say sine theta equals square root of 1 minus cosine theta. We call this one, I will put both of them in a red box, this one, or maybe in this format. Which one we can use? We will use one of them. It's also a Pythagorean identity. Same equation, sine squared theta minus plus cosine squared theta equal 1. This time let's solve it for cosine squared. We will subtract sine squared from both sides, right? You see, it's a simple algebra thing, simple math. Then you can write cosine squared theta equals 1 minus sine squared theta. And again, same way, if you take the square root from both sides, you can write cosine theta equals the square root of 1 minus sine squared theta, correct? Which one you want to use? Both of them is also Pythagorean theorem. I did a little bit proof here. You are not required in this class up to now, up to this chapter, to do any proof on the test day. I will not ask for any proof, just problem solving. I did the proof to show it for you from where this identity comes in. Now I'll do 1 or 2 examples very fast, and I think we are done with the section 1.4, correct? Let's do an example, at least one or two to practice. Example number 1. Find sine theta and tangent theta and tan theta given that cosine theta equals negative square root of 3 over 4. And they give you a condition here, sine theta is greater than 0. Hopefully you will know why they give you sine theta greater than 0. Actually, they are talking about the sine of sine, which quadrant this angle actually lies. Correct? Okay. Find sine theta and tangent theta. They should tell you using Pythagorean theorem. On the test day, I will give you even that. Which way you want to find it. Using Pythagorean theorem, find sine theta and tangent theta given that cosine theta is this. Your first identity is sine squared theta plus cosine squared theta equal 1. If you don't remember exactly which one to use, start with this. Other than that, because you are looking for the sine, I just proved for you, I gave you something ready. Sine theta equals the square root of 1 minus cosine squared theta. Here I missed a square. Cosine squared theta. Use this one. Because cosine is given, immediately you can find the value of sine. Correct? Let's do it. Let's use that one instead of using this. Because I already proved it for you. I don't want to work again. Sine theta equals a square root of 1 minus what? Cosine squared theta. If you don't remember, immediately plug in this value here and square it, solve it for sine. It's another way. Which way works for you? I prefer to use these given ones. Sine theta equals a square root of 1 minus. What is cosine theta? Cosine theta is negative radical 3 over what? Over 4, but square it. Then you can say sine theta equals a square root of 1 minus. The negative square becomes positive. When you square radical 3, it gives you 3. And when you square 4, it gives you 60. Correct? Simplify under the radical. Sine theta equals a square root of, again, the other day I explained to you how you add or subtract two numbers. You need a common denominator of 16. Let me go first your way. You have to multiply this one as a 16 over 16. 16 minus 3 gives you 13 over what? 16. Square root of 13 over 16. Now you can simplify a little bit. You can say sine theta equals 13 doesn't have a perfect square root. Keep it under the square root. But 16 has a perfect square root, which is 4. Here you go. You found the sine of theta. Correct? Next one, they are asking you to find the tangent. Using the identities that I worked on this side, quotient identities, you see your tan theta equals sine theta cosine theta, correct? Because we already know sine and cosine, I can use that one. Tan theta equals sine of theta over cosine of what? Theta. Then you can say tan theta equals sine of theta, we just found it, it's radical 3 over 4. over cosine theta. It's given in the problem, negative radical 3 over what? 4. We just simplify this. Then I can say tan theta equals radical 13 over 4 times, flip the denominator, negative 4 over radical 3. You can cancel out 4 with 4. Then you can write tan theta equals radical 13 over radical 3, but negative, correct? Now, if you want, you have to rationalize the denominator, right? I told you to rationalize the denominator, I will multiply this fraction with the denominator. It means I will multiply top and bottom with radical 3, correct? Then I can write tan theta equals radical 13 times radical 3 gives you radical 39, negative radical 39, over radical 3 times radical 3 gives you 3. Final answer. You see, by just giving one trig function using the Pythagorean theorem and using the quotient identities, you can find the rest, correct? That was the example. There are a few more in your lecture. I will not going to solve them here for you. I'll let these examples for you. Practice it, because the answer is anyway in presentations. Practice it, and I'll stop my lecture here. See you all in chapter 2 lecture.